Good morning, everyone. We'll get started here. So midterm one has mostly happened. Some of you guys are still going to take the exam Thursday or Friday night due to conflicts. If you had a conflict with the exam, your exam may still be to come. So we won't talk too much about midterm one just yet. So good luck on the exam for those who still have to take it. And probably not until Monday will we talk about exam results. I doubt they'll be posting exam scores until all the exams have been taken. My guess early next week will be when they actually open the test for reviewing the questions and checking the answers, but we'll talk about that along the way too. So let's get into chapter 4. I like to send a message on, attendance is great this morning. Occasionally after midterm one, the next lecture, attendance tends to drop off. I think this is about the usual amount that I've seen before the exam, so that's great. So appreciate the attendance. Chapters 4 and 5 and 6, the pace will start to pick up. So if you found the first couple chapters not so hard, then I think you'll find these next 3 chapters probably a little bit more challenging. If you found the first 3 chapters challenging, let's just stay caught up. I think the best way we can stay caught up here in chapter 4 is just coming to class, trying to stay up with the reading, staying up with the problems, and then just testing ourselves and getting used to the idea of trying to solve problems without a lot of study aids. Because that was probably the hardest part about midterm 1, wasn't it? Like that you can look up how to do a problem. Like that's always the hardest part on the test, is that one problem that you know how to do if you just had a little nudge. And so we just have to get good at doing problems the first time we see them. So, okay, getting into chapter 4. The topic of chapter 4 is aqueous reactions, or dealing with properties of solutions, dealing with water. So we're going to talk about water solutions. So we're going to talk about things like how ionic compounds dissolve into water. What happens when they dissolve is ionization. So we're going to talk about that process here soon. We'll talk about precipitation reactions. That's where you can take 2 solutions where they're both clear solutions. We can mix them together and form a solid and try to predict what the solid is and why that solid is forming. We'll discuss acids and bases and then get into some acid-base reactions. Then towards the second half of the chapter, we'll get into redox reactions. Those are reactions where there's change of charge taking place during the reaction. So oxidation, reduction reactions. It's kind of in the middle of the chapter. We'll also then talk about concentrations of solutions. So if we're going to prepare a solution where we take so much, say, sodium chloride, put it into water, we're probably going to want to talk about concentration units. You may have seen molarity before. If you haven't seen it, we'll talk about that towards the end of the chapter. So that's kind of like moles of a solute per liter of solution, but we'll talk about that topic later. And then we'll wrap the chapter up with stoichiometry of reactions occurring in solution. Those problems will resemble problems that you saw from chapter 3, just where we're now dealing with, the solutions. So we have to deal with the solution properties and how we use solution units when we get to that topic. Okay, so let's talk a little bit about the process of a compound dissolving into a solution, such as sodium chloride dissolving into water. And so we've talked a lot about sodium chloride not being a molecule like, say, methanol is. So we have methanol in the opposite slide, or the opposite picture. And so what's going on when sodium chloride dissolves into water is each of those ions of sodium and chloride are being surrounded by their own little sphere of waters. And what's really interesting, if we zoom in here, is that the hydrogens kind of attach or surround the chloride ion. So this is our Cl minus. The water molecule, you probably know that it's polar, or if you don't remember the polarity of water, we'll talk about this later, but water plus and minus charges develop on the H and the O's. So the hydrogens develop this partial positive charge, the oxygen atom a partial negative charge. We'll get into polarity and understanding why this happens. If you haven't seen it or forget it, we'll talk about that in chapter 8. But so water has this dipole moment, if you will, this built-in polarity, and then the positive charge of water actually is surrounding the minus ion. So we're taking what used to be a plus minus of chloride, sodium, chloride, sodium, chloride, sodium, very strong ionic bond, and we're replacing that strong ionic bond with presumably stronger forces with water. And by presumably, I mean since it dissolves, I would presume that those forces are stronger. The sodium cation, if you notice, the positive charge on the plus is then being surrounded by the oxygen atom. So the oxygen's negative charge gets that attraction with the positive. So we get this plus minus attraction when we form like a water sphere around the sodium cations, and we get total ionization. And what I mean by like total ionization is when we take like solid salt. I'm going to dissolve this into some water. I'm going to give this a minute or two to dissolve. And I'm going to take a packet of sugar. So sugar is going to be kind of like my methanol here in terms of something that's a molecular compound. So table sugar is mostly kind of resembling what methanol looks like in this picture here. We could have taken methanol too as a demo. Liquids mixing into water is actually a little bit of a different process than a solid dissolving. So a solid, we would tend to want to know, does it dissolve or is it soluble in a solvent like water? And then every solid would probably have some maximum solubility. So sodium chloride into water, I think, is like 600 grams per liter of water. That's actually quite a lot that will eventually dissolve. It'll take a while, but it eventually would dissolve into the solution. Now, methanol would just perfectly mix with water. Now, you don't have to predict or know that, but it just happens that it does. So methanol, you could take a drop of methanol, it would mix into water. You could take a drop of water into a lot of methanol, it would mix perfectly. And so methanol, the word we tend to use here is miscibility, that it's miscible. So miscible just means that these are liquids that mix in any proportion. Wrong color. Mix in any proportion. So then solubility, or just being soluble, let's use the word soluble to be consistent with the. So when we say things are soluble, this would be a solid that mixes, or dissolves is probably a better word, that dissolves So an example for solubility is NaCl is soluble in water. And then an example of miscible would be methanol is miscible in water. Or with water. Okay. So these are still working on dissolving. They eventually will. It just takes a moment of time. And what we want to compare is what happens when we take, more or less, now let's start with water itself. So if I just take, this is distilled water, and what I'm testing here is there's some way that the solution can connect the wire that would allow the light bulb to light up. And so there's two electrodes hanging down behind this little piece of plastic. They put the piece of plastic there so that I don't touch the electrode and have my body get electrocuted in the process of showing you conductivity. But water itself, you can see here, is really not conductive enough to allow the electricity to flow between those two rods. Now, that doesn't mean I should put my finger in the water. It doesn't mean you should throw a toaster into a shower or something. There's enough conductivity that you will get enough of a zap that it is not worth doing that or testing the conductivity that way. But you can see there's not enough conductivity to light up that light. Now, if I take the sodium chloride solution, even though it hasn't totally dissolved, I know that it's going to have enough ions in solution to act as an electrolyte. What's going on is the electron from the one post has electrons on it, is flowing through the ions. And so it's just flowing from the plus to the minus, the plus to the minus, plus to the minus. So the plus minus ions are acting like a wire to connect those two electrodes. If I could just take a piece of copper wire and touch the two electrodes, the copper wire would serve as the conductor to allow the light bulb to light up. And so now I have this piece here to turn off, so I can test. I can the sugar solution to see if it conducts or has this property of being an electrolyte, and it doesn't have that property. So one of the things that you can see is that just simply dissolving and making a solution doesn't allow the solution to become electrolytic. Something has to happen upon the compound dissolving that makes the solution electrolytic. For sodium chloride, it's ionization. It's the formation of these ions that make sodium chloride behave in that fashion, and then that's why we would call a solution of NaCl an electrolytic solution, because it serves as an electrolyte. It allows that light bulb to light up. So NaCl in water, that we get a strongly electrolytic solution. And it's because of the presence of those ions, of sodium plus and chloride minus, that have dissociated off of that block of sodium chloride. So methanol, C12H22O11, which is sucrose, from our example here, that the implication is that these are not electrolytes. So these are not electrolytic in solution with water. And the simple implication is that they simply do not ionize in solution. So they're not making ions in solution like NaCl did. So ionic compounds are all plus, minus, and it could be like calcium oxide, +2, -2, +2, -2. It could be NaCl, +1, -1. It could be like MgCl2, +2, -1s. So you have a variety of charges, and it's always at least +1, -1, if not even higher charged ions. So in an ionic solid, you have those strong electrostatic forces of attraction, and those electrostatic forces of attraction are just being replaced with water's electrostatic attraction. And then if water is able to dissolve the compound, the ionic compound has to ionize. So any ionic compound that dissolves into water must be doing this ionization process, because that's the very nature on how or why it's going to dissolve into water. And I think the real simple thing to keep in mind is that the sodium chloride unit doesn't remain intact in water, that this breaks apart when we go into water, that the plus and the minus ions have to separate. Now, there's no plus and minus that have to separate in methanol, and if it did, we would see ionization. If we saw like the sucrose molecule breaking into some kind of ions, it would have lit up the light bulb. We would have seen the result of that. Okay, so let's take a look at some solubility guidelines, and then we'll take a look at a couple other examples of electrolytes in a moment. But if we want to then say, can we look at the ions in a compound and predict if the compound's soluble? And the answer is we can mostly do that. That we have some solubility guidelines that will help us be able just to look at a given compound that's ionic. So these solubility guidelines are the solubility guidelines for common ionic compounds in water. So when we take an ionic compound, put it into water, can we predict solubility? We get soluble ionic compounds when the compounds include things like nitrate and acetate. So if you pair nitrate and acetate with literally any cation, then you're going to have a soluble solution. So that compound will dissolve into water, it will ionize. And so we can give a tremendous number of examples here. Some examples could be like KNO3. So KNO3, put it into water, should dissolve like NaCl. Might take it some time. It's not going to immediately dissolve. But over time, it will become soluble in the solution, at which point we'll get K plus and NO3 minus ions. And this is another detail that we have to kind of process, is that all those ions we learned how to name, like nitrate, acetate, sulfate, et cetera, that those ions stay intact in water. That nitrate's not going to fall apart to nitride and to oxide. It just stays as nitrate. Like the nitrate ion is stable in water. It exists just as that nitrate ion. We could give examples like lead acetate, Pb, C2H3O2, 2. Remember, C2H3O2 is another way of writing acetate. So this is a formula for lead acetate, that this would be soluble in water. And so if this thing hits water, we're going to get lead cations, and then 2 of the nitrate ions. So we'd have ions in solution. We'd have an electrolytic solution. So these compounds here, these would be what we call, and one of the designations we start to write a lot is these are strong electrolytes. So in water, they act as electrolytes. They're ionized when they're in solution. Now, another group of ions, chloride, bromide, iodide, the halide ions minus fluoride. So chloride, bromide, iodide mostly form soluble compounds, with the exceptions, 3 exceptions: silver, lead 2+, and then that goofy mercury 2, 2+. Like this mercury 2, 2+, let me zoom in a little bit just so we see that the Hg2, 2+, we probably remember this from nomenclature. The only reason I even threw this in the notes for chapter 2, it's in the book too, is that we talk about it here in chapter 4. So I want us to recognize this ion as that mercury 1 cation from our nomenclature. And so this is that mercury 1 cation. So a few examples of things that are insoluble would be AgCl is insoluble in water. Hg2Br2 is insoluble in water. And then something like PbI2 is insoluble in water. And so too would, we could write all 9 examples, but we could write 9 insoluble compounds: silver chloride, silver bromide, silver iodide. I think you get the picture. Silver or lead chloride, lead bromide, lead iodide, and then the mercury 1. But now, one of the weird things with mercury is it does form another common cation. That mercury 2 is actually another common cation of mercury. Silver doesn't have any other common ions, which I think is another reason maybe why we were trying to say silver only forms silver 1 in chapter 2, is so that we're looking at silver here saying, okay, what about silver 2 chloride? Is that soluble? Well, it doesn't really exist. So there's no other common salts of silver. Lead occasionally, in some situations, will form a lead 4+, but that's usually within like a highly acidic situation, like in a car battery, for example. So in a really acidic environment, you can get lead to go to 4+, but in a common solution that you can buy or salt you can buy, you're not getting like lead 4 chloride. So lead 4 doesn't really exist. Really just lead 2 is the only example. But I just want us to then comprehend or see that HgCl2, HgBr2, HgI2, these compounds here, that lead 2+ is not one of these insoluble exceptions. So these compounds here are soluble in water. And so that's the weird thing with lead. So lead forms 2 common cations. One of them forms an insoluble compound with chloride, bromide, iodide. And another of its common cations, the 2+ cation, just forms the ordinary soluble compound with those ions. And you can literally take any other metal, like name the metal cation that actually exists, like copper 2. So copper 2 chloride is also soluble. Barium chloride is soluble. Magnesium chloride, that's soluble in water. And so if you can just picture any other cation, now you don't have, I'm not going to give you a question that says, does manganese 4 chloride exist? We're not predicting existence of compounds here, because some cations exist for our transition metals, some don't. But the implication would be, if we show you a formula that's a compound, presumably it exists, then you're predicting it's soluble so long as it's not silver plus, Pb2+, or Hg2, 2+ in terms of the charge of those metal cations. Okay, so these soluble compounds are all strong electrolytes if they dissolve in water. So the solution would be electrolytic, would light up a light bulb. like we're doing in this example over here. So one other ion that's commonly present in soluble compounds is sulfate ion, so SO42-. We have 4 insoluble exceptions. Now I'm sure that the number one question in your mind right now, do we have to memorize this chart? We give you this chart. We're going to see that using this information is the key, not memorizing it, and understanding that these things, when they pair up, when strontium, when barium, mercury 1 again, and lead 2+, when those pair up with sulfate, they make an insoluble compound. When any other cation pairs up with sulfate, we would call that compound soluble. And so an insoluble compound would be like Hg2SO4, or it would be barium sulfate. So these compounds here are insoluble. We could write the other two, the lead sulfate and strontium sulfate. But then we could also recognize that while silver was an exception for chloride, bromide, iodide, it's not listed as one of the exceptions. So the implication here is that this compound is soluble. And so that this compound here in water would be termed to be a strong electrolyte. So we just have to take the idea that any other cation other than the exceptions paired up with that anion here of sulfate would be water soluble. Now, solubility isn't like really a yes or a no, and it's not an infinitely soluble. There's always some limit to solubility. Every compound will have some maximum solubility in a quantity of water, but we're just saying if it's soluble enough in water to call it soluble, we're calling it soluble. If the solubility is so low, if it's below some threshold, it turns out to be 0.01 moles per liter is how our textbook defines insoluble. But think about that for a minute. A compound, I think lead chloride is one that's relatively soluble that we call insoluble. It has a solubility of about 0.01 mole per liter of water. That corresponds, I think, to like a gram or 2. So compounds that we're calling insoluble actually can be soluble to some reasonable amount, but it's just so insoluble that we just say, you know what, we're just going to call it insoluble. When you get to chapter 17, you reinvestigate some of these compounds that have a relatively high but still pretty low solubility, and you solve all kinds of fun equilibrium problems you'll get to in Chem 1220. So it's a topic you come back to. So I just want us now to kind of comprehend that even things that we say are insoluble have some small solubility. Some of them are much smaller than others. It depends on the compound. And we're not even really getting into why these things are soluble versus like why is one compound soluble, one's insoluble. We're just trying to predict that solubility here in chapter 4. So we're not trying to understand the how and the why. What is it about this ion or that ion that makes it soluble or insoluble? Here we're just taking for granted these trends that we can pick apart from the generalities from our solubility chart. Now, we have some common insoluble compounds. So our common insoluble compounds contain things like sulfide and hydroxide ion. And so sulfide ion, hydroxide ion, compounds generally insoluble, but with the exceptions being soluble. So notice we have a flip in our table here. These are mostly insoluble compounds, but if you take ammonium sulfide, alkali metal cations, the first group of the periodic table, if you take those cations paired up with sulfide, those are soluble. And if you take calcium, strontium, barium, then those are soluble. So just to give a quick example, barium sulfide, this is soluble. Strong electrolyte. So the exception is soluble, and then the non-exceptions are insoluble. So barium, not barium, but I'm going to do an example. Sulfide is something that's insoluble. It would be something like copper 2. So copper 2 sulfide, this would be insoluble. So if I took an insoluble compound and tried to dissolve it into water, it wouldn't dissolve. That's what it means to be insoluble. And if we tried to light a light bulb up, I don't have an insoluble compound here to show you, but if we tried to light a light bulb up, there should be no ions in solution, right? So if nothing dissolved or very little dissolved, there'd be nothing to light up the light bulb. Sometimes it's a little confusing on whether you want to call something insoluble to be a non-electrolyte, but I think an electrolyte is a term that you give something in the solution. So if something's insoluble, it just isn't any kind, it's like not applicable to think of its electrolytic behavior. So something that doesn't dissolve can't possibly ionize. So it can't possibly have that term associated with it one way or the other. Notice hydroxide has the same exceptions as sulfide. Forever the book, I don't understand why they don't just group sulfide and hydroxide together because they share the same exceptions. So barium hydroxide, of course, would be water soluble, strong electrolyte, and then the copper hydroxide, so CuOH, this would be insoluble. And like I said, I'm not trying to then say non-electrolyte. I'm not even thinking about the electrolytic term. I have to have something soluble in water before I think about classifying it as being an electrolyte or not. So carbonate and phosphate also tend to form insoluble compounds. Their exceptions are ammonium and alkali cations. Now, I wish the book would do this too. The ammonium and alkali cations are just always soluble. So anything with like potassium cation is soluble. So you compare K plus with any anion and know that it's going to be water soluble. And so you could also generally say that anything with NH4 plus and alkali cations that this is water soluble with no exceptions. So nitrates, acetates, ammonium, and alkali cations are really the groups of anions and cations that will always form a soluble compound no matter what they're paired up with. That's just helpful because potassium, sodium are common cations that you see from the alkali group. You pair them up with any anion, you know that it's going to be a water-soluble compound. Kind of answered this question on the previous slide, so I think we'll take a look at this one together. When I was doing KNO3 in my head, I'm like, oh, that's the next example. But when K plus NO3 minus, this AQ symbol is what we mean to mean soluble. Like this is like mixed in water, is what AQ means. This means aqueous. And so when you see KNO3 aqueous, what we have to process is that my process of thinking is that this is an ionic compound. AQ means it's mixed and dissolved in water. So this is actually telling us that it's soluble, that only a soluble compound would be an AQ. And then, of course, it forms K plus and NO3 minus. So the ions we get in this solution, of course, are just those underlying ions of K plus and nitrate. I want us to be really, and I don't, honestly, like on a test question 4 weeks from now, if we put this on a test, I just know like 25% of the class is going to think that nitrate for some reason falls apart into nitrite and oxide. Like these polyatomic ions stay together. They don't break apart into their constituent ions, and even if they did, the charge wouldn't balance right to be like N3 minus and O2 minus. It'd have to go like N plus and O, you know what I mean? Like it's just know that that's for some reason a weird distractor that is easy to think maybe these polyatomic ions dissociate in solution. They don't, they stay intact. And the only reason none might be an option is if the compound were insoluble. So if we're thinking of something insoluble, we might be thinking none. And then we're also, like if something is insoluble and you just said, well, I thought you said it might have a tiny bit of solubility, so would there be some ions? We usually don't get into that nuance. In chapter 4, we're just like solubility is either there or it's not. So we're just assuming soluble or insoluble and not getting too tricky on the little nuances that even something like PbCl2 might have some reasonable concentration in water. Let's take a look at this question here. Let me actually throw this one to you guys for a minute to try to digest the chart, see if you can put it into use to try to figure out which groups of these ions are all insoluble in water. All right, let's take a look here. So the first group of compounds, Hg2 plus, chloride minus, that's water soluble. That's not one of the exceptions. So this is soluble, that's not insoluble. Lead nitrate, all nitrates are soluble, so that's not insoluble, that's water soluble. Anything with K plus is soluble, so that's soluble. Anything with an alkali cation, and also that's an exception listed for sulfide. So all 4 of the options in A are water soluble. And group B, Hg2 plus, so Hg2 plus is an exception for sulfate, so that is insoluble in water. AgBr is indeed insoluble in water, that's the exception for bromide. Calcium carbonate, calcium is an exception for sulfide and hydroxide, but not for carbonate and phosphate, so this is also insoluble. And then copper hydroxide, we did an example earlier, that's copper 2 plus, hydroxide minus. That's also insoluble, not one of the listed exceptions for hydroxide. So all the groupings in B are insoluble. And then what about the options in C? 2 plus minus, this is an insoluble exception. Silver sulfate, though, is soluble, according to our chart. So silver is not listed for sulfate as an exception. It's listed for chloride, bromide, iodide. We just have to be careful to use the solubility chart to see that silver is not listed for sulfate. Barium hydroxide is also water soluble. NH4PO4, so ammonium phosphate is also water soluble. These choices, again, we might have to make sure we're seeing our chart. The bottom chart, mostly insoluble. The exceptions listed are soluble. So only one in group C was insoluble. So the answer to this question would be B. So that's like one question or type of question on using the solubility chart to predict solubility. Now, another way to use a solubility chart is to try to predict when we have a precipitation reaction taking place, often what we call a metathesis or exchange reaction. The basic idea here is if we take like an AX where we have some like plus minus and we have a B Y, let's say we have another plus minus, that we're considering these solutions in water, and we're picturing these as ionic compounds. So these are compounds that are ionized in solution. So we're picturing starting with aqueous solutions where those compounds were soluble. So hence we had AX in solutions, we had A plus and X minus separated and ionized in solution. We had BY separated in solution. And then do you get the exchange of these cations and anions to get AY and then plus BX? And what you have to have is at least one of these has to be a solid. And we can even throw in or a gas. For metals, I don't think we're going to form a gas. This might come up and be thoughtful in an acid-base thought when we get to acid-base reactions later. But we have to have something that leads a reaction to take place. Because we're mixing ions. So AX and BY, those are just be solutions of ions. And if I mix solutions of ions and nothing precipitates out, I end up with solutions of ions. I don't really form anything. And so at least one of them has to form a solid. That's with ionic compounds usually what we get. When we start taking acids and bases, you can get a gas that forms. You can form something like water or something you have to form something that doesn't go back and ionize. So we're looking for something that forms a solid, something that forms an insoluble precipitate. So let's start with something where we don't get a precipitate, just so we can picture what it means to have no reaction take place. If I take NaCl, so plus minus, and I react this with like KNO3. And by react, I just mean mix. So if I take these two solutions and mix them together, sodium chloride, just a clear solution, KNO3 is another clear solution, mix them together, and I'm thinking, do I get KCl to form, so the new plus minus, but this is also water soluble, and then I would get NaNO3, also water soluble, also AQ. So both of these compounds are water soluble. Do you see how no reaction has really taken place? Even though I can write like molecular reactants and molecular products, what looks like, what I mean by molecular is I can write these formulas that really don't form in solution, because really what forms in solution here is Na plus, Cl minus, plus K plus nitrate ion, that we just have free ions in solution. Even though I'm writing KNO3, KNO3 is not in solution. What's in solution is K plus and nitrate ion. And that these are reacting to form K plus, chloride, sodium, and nitrate. That I'm just forming these aqueous ions. Now I can write this AQ tag for all of these. Often, and probably after this slide, we will just take for granted that if you have a charge in water, it has to be surrounded by water. That's the nature of the process. And just to save time, I'll be writing like chloride, usually not AQ every time I see the ion. If you have an ion in solution, it has to be AQ. It has to be surrounded by water is the implication. But you notice how there's no net change, that there's no actual reaction taking place. So no reactions occurred within this solution. And so I have to get the formation of something that's insoluble from the mixing of solutions. So let's take a look at another example. So an example of silver nitrate. Silver nitrate's water soluble. Anything with nitrate's water soluble. Let's mix this with KCl. Also water soluble. And now we're just doing the exact same thought. I'm just doing the plus minus switch, and I would get AgCl. Now, should I write AQ or solid, and why? Solid, because this is insoluble in water. So what we're thinking here, is this soluble or not? And the use of our solubility chart is where we're getting insoluble. So if I take these solutions, mix them, a solid forms. I think you've already done a reaction like this in lab. The PBCl lab was doing this. And so you're forming the insoluble precipitate. It falls out of the solution, generally just because the solid's more dense than water, so it floats to the bottom of the test tube, or you use a centrifuge or something to speed that process up. And then you get the counter product of KNO3, which is water soluble. So for our products, we're just thinking, are they soluble or are they insoluble? Now, often the whole idea of the process is you should generally begin, or usually the problem starts with the solutions being given to you, so you know you're starting with compounds that are water soluble. And what we could also know that AgNO3 is water soluble, is the same with KCl. So it's the formation of the solid that drives there to be a net change. Now, there is a process for trying to write the net change in that ionic equation. Like, what is the actual net change taking place? This usually comes from thinking of the ionization process. So if we're thinking like we did previously, we have Ag plus, NO3 minus, plus K plus Cl minus, that's really what the solutions look like at the ionic level for silver nitrate and KCl. We call this reaction here, this reaction is what we often call the full, and I like to put this in quotes, molecular reaction. And full molecular kind of means we're writing the reactants and products like they're molecular, even though they're not. Like, we're thinking that these water-soluble ionic compounds dissociate into those solutions. But oftentimes, and we'll use this all the time, we'll say like KNO3AQ, even though we know it's K plus AQ and NO3 minus AQ. But just colloquially, we call that the full molecular reaction. And then if we think about the ionization going forward, we don't break apart the AgCl because it's not an electrolyte. It doesn't dissolve in solution. It doesn't ionize. It's in its solid form, not in its AQ form. So the plus and the minus in silver chloride go Ag plus Cl minus, Ag plus Cl minus, Ag plus Cl minus. We get that nature of the solid, and then K plus nitrate. And so if you notice here, K plus and nitrate are kind of just watching the reaction. They're not changing. So these are unchanged during the course of the reaction. We call those unchanged ions the spectator ions. They don't disappear. They don't annihilate. This isn't some cool physics concept. This is just literally us trying to say, what's the net change? the net change wouldn't include the spectators that are unchanged. So if you imagine canceling out those things that aren't changed, we get our net ionic reaction for just the actual net change in the reaction of Ag plus chloride going to AgCl. To be honest, I don't know why this is such a big deal. Like, other than just picturing what goes on. You know, like writing the net ionic equation helps us picture at the ionic level, the solution level, what's going on. It helps us see that the AgCl, and the whole point of this is that it's not ionizing, and that's why we get this net change. So I think it helps us see that for a reaction to occur, there should be a net change. If you go back to the previous example, all those ions were spectators, and so hence no net ionic reaction occurred, so no reaction occurred. So it helps us picture what goes on in the reaction by writing these different types of reactions. So we have our full molecular, which I think is the most common type that we tend to write, and then our full ionic is actually what we would call the middle one. This is the full ionic reaction. And then often we're only writing that one to get to the net ionic. So if you have a question on the homework or on a test that's asking you to write a net ionic, usually you would think of going, write the full molecular, think about solubility to see what's solid, what's AQ, and then try to write the full ionic, and then try to cancel out your spectator ions. So it's just this process of full molecular to full ionic to net ionic, and identifying those unchanged spectators in the process. Okay, so the next slide, this is kind of where I think I was intending to write this. So this is just, you know, where we can think about the full molecular into the net ionics from that full ionic reactions identifying the spectator ions. So let's think of which solution, when mixed with strontium nitrate, yields a precipitate. So we're looking for strontium 2 plus and nitrate, NO3 minus. Now, nitrate is soluble with anything, right? So I'm not picturing nitrate, so like calcium nitrate, lead nitrate, KNO3, KNO3. The nitrates are always soluble. It's the strontium. I'm looking for, when does strontium 2 plus pair up with something here to make an insoluble compound? Like strontium acetate, an A. That's water soluble, right? Because all acetates are soluble. So A doesn't form a solid. If I take another acetate, now sometimes you see lead and you think, oh, well, lead's insoluble with like everything. Not with everything, not with acetates, not with nitrates. So if we mix lead nitrate, that's soluble. Strontium acetate is soluble. So B doesn't work. What about C? Strontium hydroxide. Well, what about that? Is strontium hydroxide soluble or insoluble in water? If you go to the solubility chart is what I would say, and you have access to the solubility chart on exam, so check the solubility chart, and it's AQ. Strontium is one of the soluble exceptions for hydroxide. So it can't be KNO3, but then of course strontium sulfate is one of the exceptions for sulfate that's insoluble. So barium and strontium, sulfate insoluble with sulfate. So when we mix K2SO4, AQ, with SRNO3, 2, which is an AQ, water soluble, that we'll get an insoluble salt that forms. All right, so let's get into the topic of acids and bases and start thinking about some of their electrolytic trends. So let's start with, let's actually start with water. So this is actually kind of a neat example here. So is water itself electrolytic? So we've already done this, but it's not, right? So we take water, doesn't light up the light bulb. Now, how many of you guys remember the auto-ionization of water to H plus and hydroxide ion? Anybody remember that topic? That's where you get pH from, or POH and those concepts. So, but if you remember anything from pH, the concentration of H plus in pure water is 10 to the minus 7 molar. Does that sound very soluble? No. So water is not dissociating to a very large extent. This is tap water. This is actually kind of frightening in a way. So this is water they got out of the tap. Okay, maybe it's not, oh, there it goes. Look at that, can you guys see that? So there's a tiny bit, I mean, this is mainly minerals, it's really not that bad. So for the small mineral content in water, you can get a little bit of that light bulb to light up. So tap water, slightly electrolytic from the ions that are present in water. So probably a little high chloride. That's mostly why you want to filter your water, to get the taste out. Well, okay, let's take a step back. There are a lot of bad things that could be in water you want to filter out. Chloride's the one that tastes bad. That isn't necessarily harmful, but it doesn't taste very good. Okay, let's go to HCl. So hydrochloric acid. Do you guys think the light bulb is going to light up? Probably. So it does. It's pretty bright. I have this solution here to clean off so that we're not just getting residual ions from the previous solution. Let's go back to water. Let's make sure I've rinsed enough of those ions off. Okay, so we're clean. What about acetic acid? Do you think it's going to light up bright as HCl? And so not as bright. If I go back to HCl, much brighter, just to see the side-by-side comparison. And so just being an acid doesn't necessarily have the same effect. If I took just about any water-soluble ionic compound, not just NaCl, it would light up just as bright, just to give you an idea that all of our soluble ICs are going to light up the light bulb almost as brightly as each other, but two acids are lighting up the light bulb a little bit differently. And let's lastly get into things that we think of as being bases, and we'll define what makes something an acid versus a base. I have sodium hydroxide. This is another water-soluble ionic compound. So just like NaCl, very bright. If I contrast this with ammonia, it's kind of like acetic acid, where it's not very bright. So just trying to clean off some of those solutions. Okay, so let's talk a little bit about acids and bases here. So we have things like hydrochloric acid, nitric acid, sulfuric acid, acetic acid. We have all those acids we learned how to name in chapter 2. That some of them are strong acids in solution. So these three here happen to be strong acids. We'll define the 7 strong acids in a minute. So a strong acid is like a strong electrolyte. It completely ionizes in water. And so HCl in water is 100% H plus and Cl minus. So we get 100% conversion to H plus and Cl minus. We could take nitric acid. In AQ, it's really 100% H plus and nitrate ion. Now let me even, right, because I think thinking 100% yield is like a nice way of thinking about this. That we get just 100% yield of those reactions. And if we look at H2SO4, when it's in water, it's really 100% or nearly 100% H plus and actually HSO4 minus. And then that second step, oddly, is only one that occurs to about 10%. So the second H plus falling off in solution only occurs about 10% of the time. The percentage depends on concentration. It's not really the point to know the specific percentage for the things that aren't 100. It's just the picture that not every acid is going to be 100% dissociating in water. And so we might look at HSO4 minus and give this a different term. I'm going to call this to be a weak acid, since it doesn't completely ionize to H plus and SO4 2 minus. So H2SO4 is a strong acid. So it's strong in its first H plus falling off, just weak in its second H plus falling off. Nitric and hydrochloric, these are strong acids. They're also strong electrolytes that we could say, because they're making ions, it's just they're making a specific ion of H plus. So this is really what makes something termed an acid, is when it's releasing an ion that happens to be H plus. That's the term that we give something to be an acid. And now, what do you think, I think we know, what do you think the implication is of acetic acid? Do you think it's strong, or do you think it's weak? It's weak, so this is a weak acid. Now, why is it weak? Well, this is completely circular, but it's weak because it just doesn't fully dissociate. And sometimes we show that with like this forward and backwards arrow. So sometimes we can go back to HSO4 minus and show this too, that sometimes we'll write this like equilibrium arrow, like forward and backwards, to indicate for equilibrium, or the case we don't get 100% yield, what's usually happening is that we're forming the ions and they're reforming the reactants. And you're just getting this back and forth where you don't get the back and forth. H plus and Cl minus dissociate, and they effectively never reassociate. And so what's really happening with the strong acids is that the reassociation just never occurs. You just never get the back process. And then you're just getting this back reaction when you have the weak acids reacting. And so then we're forming acetate, which would make sense, right? That we'd form the ion we learn how to name. And we learn how to name it because it's a stable ion. And the H plus falls off of the acetate ion because of that stability of acetate ion. So we get H plus and acetate, and we just get this to, again, about probably 5% yield or so in that ballpark. And again, it depends on concentration. The point isn't predicting the percentage. It's just seeing that it's not 100 or anywhere close to 100. So this is a weak acid. And then the weak acids are weak electrolytes. So we can give this term here, this property of being a weak electrolyte. Cannot spell. Weak electrolyte. So weak because it partially is making ions. Now, HSO4 minus is tricky because it's already an ion, and it would make more ions. So I don't get into the business of calling something that's already ionic an electrolyte because it's already in ionic form. So I don't go back and start to think about, do I call this thing here a weak electrolyte? That's complicated. It's already an ion. It's already behaving as an electrolyte in solution. It's just going to become even more of an electrolyte if it dissociates again. So for the things that are molecular, for the things that have no charge, it makes sense to classify those substances as being weak or strong electrolytes. Now, in terms of bases, sodium hydroxide making Na plus and OH minus, it's the OH minus that allows something to be termed a base. It may seem strange at first, and you probably recognize this, but the reason why H plus and then OH minus is what we call the acid versus base is H plus and hydroxide combine to form water. So OH minus is the other part of water. So anything that makes hydroxide ion in solution, we call it to be a base. This is an ionic compound, water soluble. So water soluble ionic compound, therefore it has to be a strong electrolyte. Because it's releasing hydroxide, it has to be a strong base. So you see this like process of, I'm recognizing ionic compound that's water soluble from our solubility trends. It happens to release hydroxide ion, so it's also a strong base on top of already being a strong electrolyte. And so then for ammonia, from the example we did today, ammonia does this partial reaction with water, where it's forming ammonium, NH4 plus, and then hydroxide ion. So it's making some hydroxide to about 5 or 10% yield, getting that equilibrium. And so this is where you're looking at NH3, partial formation of hydroxide ion. So this is a weak base, weak electrolyte. All right, the next couple slides in the notes will review this, and that'll be a good starting point for next week, is just rehashing and trying to figure out what are the strong acids, what are the weak acids, how do we recognize weak bases, etc. All right, guys, that's it for today. Have a great rest of your day.